Okay, so we're going to finish up just these last 3 slides. We're going to do the harder ones in class tomorrow. I just wanted to get to the easy stuff that you guys, I'm sure, are fine with, or will be better with. We'll do the harder stuff tomorrow. So wrapping up, we ended up with this slide here. Now, we already just said that when we have a collision, the total momentum of the collision, when we look at their individual momentums, if we're looking at 2 people colliding, their individual momentums just before the collision should equal their momentums after. So in this case, we're talking about the total momentum of the whole system, which is their 2 momentums added together. So again, this is going to kind of look similar to adding like kinetic energy plus potential. It'll look like that, but it's 2 separate momentums giving us a total momentum of the whole system. So I prefer to use, I don't know why, I do know why, I forgot to reopen it, that's okay. This gives us 2 versions of a formula. I prefer to use this version. P initial equals P final. This means the total, I should say P total initial equals P total final. I prefer to use this, especially when we're going to deal with tomorrow, breaking down into components. Gets really confusing because technically we can also use this as if we move over P initial, we can say that 0 equals P final minus P initial. And again, this is momentum. Momentum final, I should say that. Momentum final minus momentum initial. So again, this looks very similar. This is actually the change in momentum, right? It should be 0 because it is conserved. There is no change from right before the collision to right after. Again, I'm mostly going to be using this version because you'll see why later. It's going to get really confusing when working with X and Y components if we have everything over on one side. So with that in mind, again, because momentum is a vector, if you guys recall, vectors have components, right? X and Y components. We will need to, tomorrow, break down any of the angle vectors. If something is coming at an angle and leaves at an angle, that happens a lot in billiards, for example, we have to break down those components. So we got to be really careful with that. We'll look at that in class tomorrow. For right now, we're not dealing with any angled vectors, though, so we can ignore X and Y components and just look at these separately. So this example is on page 379, but we can just kind of look at it here as well. So Gordy, a 100-kilogram hockey player, is initially moving to the right at 5 meters per second. So here's Gordy going to the right at 5 meters per second. Hello. Yes, this is Tracy. Hi, is this Janice? Hi, I'm good. I'm so sorry for playing phone tag. No, I know. I know, and then yesterday I was helping some students after school, and I was like, oh, crap. So that I missed the phone call again, so. But I'm good now, yes. I did actually respond to the email an hour or 2 ago. I had a chance for that as well. I hope so. Do you see it? Okay. Let me hope that I click send and not left it as a draft. Let's see. Okay. Yeah, it says it went through at 1:20. If you want, I mean, I can just go through. It might just take a while to go through. I did send over the appraisal waiver and the calendar year pay for the HOA. Our HOA doesn't have a website, so they send us like the paper copies. I don't keep them, so there'll be one coming again soon, and then I can send it over after that. Yes, just he's not going to be on the loan. Yeah. So that was weird. So I made a whole explanation in the email. So I actually teach at the high school that I graduated from. So my my senior year of high school, which was that 6/1/2009, that was the summer before my senior year. I got hired as a tutor for summer school, and then the May, or I guess the June after I graduated, I got hired as a coach. So I started coaching right after high school, but it was just part-time. I didn't start teaching until 2014. So I've technically, yeah, so I'm not sure what you need to quantify that as. Right. Yeah. They would have had my social security on their record, my number on their records, I guess, since I was in high school. So officially as a full-time teacher, that was July 2014. Yeah. Dow is my maiden name. Yeah, Dow is my maiden name, which is my email is still, yeah, using my maiden name. I just never, this was my email in college and it just became my personal email afterwards, so. Okay, I can try and resend it, yeah. And then again, I'll still need to send over the HOA statement anyways, so yeah. Okay. Okay. Sounds good. Thank you so much. Okay, bye. Okay, where was I? Okay, so Gordy here is traveling to the right at 5 meters per second directly towards Mario. So I'm going to call this Gordy and I'm going to call this Mario. It is really important that you guys label on these the directions, because remember, because we're now dealing with vectors again, we haven't dealt with vectors in a while because energy was not vectors. We have to call a direction positive and a direction negative. So we are going to go ahead. I'm going to go ahead. You don't have to, but I'm going to call Gordy a +5, which means going to the right is positive and traveling to the left is negative. So that's important because when it says in what direction, if we do our math and we end up getting a negative for Mario, then that would end up, I should say, we do our math, it's Gordy. So after the collision, we're looking for Gordy. If we end up with a negative, that means he is now traveling to the left because we said right is positive. So we're back to being very careful with our directions. So this was before. This was the before picture. He's going to the right and Mario is stationary. After, which is always kind of a good idea to draw this, you'll see it tomorrow in the notes as well. They give you a before and after picture. After Mario is traveling to the right at 3.75 meters per second, we are going to look for how Gordy travels after. Yeah, this is kind of our question mark here. So what we know is that the total momentum, both of their momentums added together initially, the total momentum is going to equal their total momentum afterwards. So what we're going to do again, our total momentum from before. So this is the initial, right? So I'm going to call this P Gordy initial plus the momentum of Mario initial is going to equal the momentum of Gordy final plus the momentum of Mario final. And again, we could use it where they're on the same sides, but this will be easier dealing with momentum, like I said later, to keep the initials on one side and the finals on another side. Now again, their individual momentums can change and will. Their individual momentums will change. What does not change is the total. When you add them together, that's the same. So we have Gordy's mass times his initial speed. I'm going to call that GI. We want to be careful here. Plus Mario's mass times his initial speed equals, equals Gordy's mass, I'm going to keep saying the wrong words, times his final speed, and that's what we're looking for. What speed is Gordy moving after the collision, the final, plus the mass of Mario times his final speed. Mario, final. So I want you to take a moment. I'm going to scroll a bit here again. Plug our information. We know all of the info except for Gordy's final speed. Now again, if it ends up being positive, that means he's traveling to the right. Because we said the right direction is positive. He is moving to the right. This is a positive 3.75. If we do the math and he ends up negative, he's moving to the left. So go ahead, plug our information in, see if you can solve for Gordy's final speed. Okay, so the mass is 100 kilograms for Gordy. His initial speed was that 5 meters per second. Plus Mario's initial mass was 80, but his initial speed was 0. He was not moving, a stationary 80 kilogram player. So we're going to ignore that eventually. The mass of Gordy is 100 times, we're looking for his final speed, plus the mass of Mario is 80, and they tell us his final speed was 3.75 positive because we're going to the right. I'm going to go ahead and give myself some space here. Okay, so let's simplify this. We got 500. 80 times 0 is gone. We have 100 times Gordy's final speed plus 80 times 3.75. So 80 times 3.75 is 300. And then we just got to solve. So minus 300. We get 200 equals 100 times VGF. We're dividing by 100. We get that Gordy's final speed, his final velocity, I should be clear here, is a positive 2 meters per second. So because this is positive, does that mean he is traveling to the right or the left? He is traveling to the right because we initially said that right is positive. If we did the math and it came out to be a negative, our answer would be to the left. So it says, what was the change in Gordy's momentum in the collision? So we need to know his change in Gordy's momentum. We know how to do this because we've done change momentum many times. We're looking at just Gordy. What was his final momentum minus his initial? Just his. So take a moment. I'm going to write one more thing. The change in Gordy's momentum is going to be his mass, Gordy, times his final speed minus his mass, because that's the formula for momentum, times his initial speed. So go ahead, you should have all the information. Plug it in, see what the change is. Okay, so his mass was 100. His final speed we just found to be 2. Minus his mass here is again 100. Times his initial speed, which was 5. So if you notice, because he slowed down, this is 200 minus 500. That was a 300 kilogram per meter per second change negative. So he lost some momentum. He collided with him and then kept continuing in the same direction, but slowed down a little bit, right? So he lost some momentum here. And that was actually how much momentum he did lose. Again, he was still traveling in the same direction. It's just that now it's a little bit slower. So the change in Mario's momentum, we're going to do the exact same thing. So I want you to try it again. Change in Mario's momentum is his final minus his initial. Go ahead and give this one a shot, and then we'll come back and check. Okay, so Mario's is Mario's mass times his final speed minus Mario's mass times his initial speed. So his mass was 80. His final speed, they told us to be what again? 3.75. That was his final speed. Be very careful here. Minus Mario's mass times, hey, his initial speed was again 0. So 80 times 3.75 is a positive 300 kilograms times meters per second. So Gordy gained momentum. And if you notice, look, the exact amount that, Mario, the exact amount that Gordy lost, Mario gained. This is conservation of momentum. The exact amount that, again, he lost got transferred into Mario's momentum. This is what it means by conservation, right? The total is not going to change. Gordy started with all the momentum, transferred a little bit into Mario, but the total is the same. So I want you guys to go ahead and try this next one. It's going to be the exact same situation. We want the girl's speed after the shove. We are going to start with the total momentum to start with. So we have the girl's initial momentum plus the boy's initial momentum is going to equal the girl's final momentum plus the boy's final momentum. Go ahead and give it a shot. We'll come back and check. Okay, so let's expand this a little bit. We've got the mass of the girl times her initial speed, G initial, plus the mass of the boy times his initial speed equals the mass of the girl times her final speed, velocity I should say, you need to be careful with that still, plus the mass of the boy times his final velocity. Yeah. Okay, so we're just going to plug everything in. The mass of the girl is 40. Her initial speed is standing at rest, so 0. Careful with that if you're a little confused. Plus the boy is 60, who is also standing at rest. Hey, both of their initials are 0. And then we have the after. After, the boy is moving backwards at 2 meters per second. So we're looking for the girl's speed, so I need to be careful with how I plug this in. The mass of the girl is still 40. We are looking for this, right? Her speed after, plus the mass of the boy is 60. Now, we need to be careful how we designate this. The boy is moving backward at 2 meters per second. You can call that this direction or this direction. We don't necessarily know what backward is. You just have to say, if you want to call this positive, keep in mind that if we do the math and the girl's speed comes out to be negative, that means they're traveling in different directions. So I'm going to go ahead and call this 2 positive. It's okay if you called it negative because you think backwards, okay, it's negative. What's going to end up happening is our answer for the girl will end up reflecting that. So I'm going to go ahead and say that his final speed was a positive 2. You could have said negative. Okay, so this equals 0. So that actually all cancels out there. We got VGF plus 120. Yep, so we can see what's going to happen right here. The girl is going to go the opposite direction. We have negative 120 equals 40, her final speed. So she ends up with a final speed of negative 3 meters per second. So again, what that means is she's traveling in the opposite direction of him. As she pushes, because they're both at rest on ice, you can probably imagine this. She pushes away and goes backwards while he goes that way, away from her. They're going to go opposite directions. So again, just being careful. There's a lot of little labels, but especially tomorrow when we start dealing with components, you need to label these very carefully. I know it looks like a lot, but if you do not do labels like this, where you have the person and initial, the person final, or whatever it is, you're going to get even more jumbled up. So hopefully that makes sense so far. Tomorrow we're going to do some harder questions.